Uh, Good afternoon, everyone. My name is Sarayoot Netsakkasame from Department of Mining Engineering, Chiang Mai University, Thailand. My topic today is groundwater flow modeling for pitfall stability and for heap analysis, a case study of Mammoth Mine. Our main activity are in the field of dewatering in Mammoth Mine, which is also my job in Mammoth Mine too. Mammoth Mine is the biggest open pit coal mine in Thailand and located in Lampang in the northern part of Thailand. Mammoth Mine serves lignite as fuel to Mammoth coal-fired power plant with a 2,400 megawatt generating capacity. Mammoth Mine has the total economic reserve of coal 800 million tons. The coal production is about 16 million tons per year. The mine with the maximum width of about 4 kilometers and the length 7 kilometers. This is the picture show the active mining area looking from north to south. At present, the pitfall is about 300 meters below the ground surface. And I will explain the hydrogeological of Mammoth Mine. Left picture show the hydrostratigraphy of Mammoth Mine can be divided into three formations. The upper is a Hue Luang formation is defined in local minor aquifer. The middle is a Na Kham formation is defined in aquitat, and the bottom is Hue King and Basement formation is defined in major aquifer located underneath the Mammoth Mine. The right picture shows the groundwater flow direction move from north to south by topography. The study area, the up picture is a cross section and below picture is a long section across the central part of the basin. If we mine total lignite out, the burden load over the aquifer will reduce. If we cannot pumping water out of the Mammoth Mine, groundwater pressure can affect to mine operation because the groundwater pressure is still high. The objective of study, the first, develop groundwater flow model in order to understand aquifer and groundwater pressure effect Mammoth Mine deep open pit coal mine. The second, to analyze pit wall stability in C1 west wall and for heap problem against groundwater pressure. Final, make dewatering and depressure plan continue for the Mammoth Mine life. Using groundwater flow model. Let's move to the next part for heap analysis. Factor of safety against groundwater pressure by simple weight balance model. A factor of safety is a resisting force divided by divide force. Groundwater pressure is divide force and overburden load is a resisting force. In this equation, we assume side friction is zero. It is a general effect that the overburden load is represented by unit weight of log multiplied by overlaying material, and the groundwater is a unit weight of water multiplied by groundwater head. Let's move to the result of for Heave analysis. From the calculation and plot in contour line factor of safety. From the critical area of for Heave, it shows the area that factor of safety less than 1, or critical area in a red color. Red color it means problem area or critical area. From the result in the left picture, the critical area begin in 2038. The problem is also small at the central pit, and then the problem area is wider until the end of mining operation in 2048. The next part is slope stability section. Analyze slope stability at C1 west wall. In this area, have measured it for displacement about 250 meter. Result in the P-slope is deep and steep. The major eastern for half-dip angle 65 degrees, which co-layer half-dip slip down to deeper. It is necessary to reduce the P-slope about 250 meter high, with overall slope angle 17 degrees. And then slide analysis slope stability use the method of slicks. It is based on the limit equilibrium use Morgenstern-Pike method by Log-Side slide to the slope stability software. Analysis cross-section N11 to N18 in C1 westward indicate that in the year 2026, there has the potential to begin slope stability problem against groundwater pressure. Show sample of analysis cross-section N11 in this picture. You can see factor of safety 0.8 or less than 1. It means this slope can failure. From slope stability analysis in 2026, approximately 4.5 cubic meter of block mass will begin to fail. When the digging and unload price is 80 baht per BCM, the damage volume is about 344 million baht or about $11 million. The volume of mass slide will increase with the failure boundary extend until the end of mining operation in 2048. This picture shows seepage from groundwater in the pit in Mammoth Mine. Pit 4 is the groundwater disrupt the mine operation. And another example of seepage groundwater flow through the structure plane, like joint fall and bedding plane. Seepage may cause the pit slope instability. If cannot pumping water out of the pit, it may cause slope stability and for heap problem. The final part is a groundwater flow model. It used to plan to dewatering out of the pit. This is show the workflow for build groundwater flow model. The groundwater model based on the mud flow. It a 3D multi-layer cell center and finite different saturated flow model. Setting up 3D groundwater flow model using GMS software and special design to a groundwater flow model in Mammoth Mine. The conceptual model in the left picture surround an area of dimension 44 square kilometer have 4 number of geological units. And after that, the conceptual model is translated into a numerical model in right picture. It the finite element grid 101 row, 74 column and 5 layer. It consists of 46,000 nodes and 37,000 cell orientation parallel to Mammoth Mine, as well as the boundary condition, initial condition, aquifer parameter, and hydrogeological state are assigned. And then the model simulate in transient state and calibration run into prediction. If man observation volume has been assigned to mud flow, the calibration error at each time step can be plotted using a calibration target in upper left picture, and in lower left picture the observation target error bar. The color bar represents the error. If the bar within the target, the color bar is shown in green color. If the bar is outside the target, the bar is yellow. And if the bar is outside target more than 200%, the bar is a red color. And the light picture time series plot use 10 observation well sample comparison in 15 observation well in 4 years. Can see most of calibration target is shown in green color. It means that a good result. And by comparison, contour line of groundwater level between measure and calculate in each year during the calibration period of 4 years. It found to be consistent, such as comparison contour of groundwater level on January 1st, 2017. And the root mean square of groundwater level between measure groundwater head from 10 observation well and compute groundwater head in calibration time for the final calculation is in the 1.36 shown in the left picture. This leads to an accuracy about 98%. And right picture show the detailed water balance in every time step. During calculation, the blue color of graph means the water flow in the model. Most of groundwater flow in from basement formation or from aquifer. The red color of graph means the water flow out. The most outflow by pumping well. After model calibration, the groundwater simulation ran to predict dewatering in the basement formation. The predictive simulation is applied at 1 year interval from present to the final pit in the 2050. Sample predictive simulation of PA15 observation well in left picture, and the right picture show the detailed water balance every time step during prediction. Exam during the calibration, most of info from basement aquifer and most of outflow by pumping well. The left table show the result dewatering requirement, total water balance, and target drawdown in each year. The result show that the future dewatering requirement from present to the end of mining operation are average 5,153 cubic meter per day, or 1.9 million cubic meter per year. In the right picture show the groundwater level will be lower than the lowest peak for in each year until the final state plan to ensure safe mining in for heap and slope stability condition. And the final is conclusion. The first, the groundwater in basement formation is important geotech factor in Mammoth Mine, especially in the deep mining operation. The second, slope stability problem against groundwater pressure is also likely to begin in 2026. Critical area of for heap problem is expected to be begin from 2038 to the final pit in 2048 as the degree of problem area become greater. The developed and calibration groundwater flow model fulfill requirements. The accuracy of model is 98%. The comparison of groundwater contour line between measure and calculate provide good result. And the final, the simulate suggest that dewatering requirement average 5,153 cubic meter per day for depressurization to ensure safe condition. As for the slope stability and for heap condition, groundwater dewatering system can be installed in production well. Exit groundwater pressure under the mine floor can be reduced continue until the end of Mammoth Mine life. Okay, I will end of presentation. Thank you for your kind attention.
Right, thank you, Dr. Sarayoot. Now I will open the floor for questions. So, any questions from the floor? Anyone?
I have one question.
Okay.
Dr. Sarayoot, You use CFD to simulate. Use CFD for the simulation, right?
Simulation in slope of or for heap or groundwater.
Groundwater.
Yes, I use GMS software by finite different grid.
Finite difference grid. Okay.
Yeah.
And how many grids do you use to simulate that groundwater?
Grid is about I use 46,000 node and 37,000 grid cell.
37,000 grid cell.
Yeah.
Okay. And how big is your domain of the simulations?
44 square kilometer.
44 square kilometers.
Yeah.
Okay. Have you tried refine the mesh? How can you be so sure that your result is accurate? Because you have 37,000 grids for 44 square kilometers. That is, you mean is your grid is very large. It's quite a cursed grid. Or is that you reached any limitations?
I refine grid in the pumping well only.
Only in the pumping well only.
Oh,
okay. All right.
Yeah.
Okay. Because I think it's interesting to refine the grid more. Maybe we can use up to 100,000 or something like that, or even more to check because we have a very big areas, 44 square meters. That is very huge. If I don't know, from my experience, if we refine the grid, then we will find a different result. So yeah, you should try that. Yeah, thank you.
Thank you.
Thank you. I have a question for you also.
Yes.
Do you conduct the grid independent study or mesh independent study to see whether if you change the grid, will that affect your result?
The grid is the material type for the again, please.
I was asking if you change or you increase or decrease the number of grids.
Okay.
How will that affect your result? Will you get the same result?
The same result.
Yeah.
The grid is small in the pumping well and extend outside the boundary in Mammoth Mine.
I see. But maybe you didn't get me. Yeah. But it's okay. How about how close the modeling of the groundwater compared to the real world environment? So how do you check that? Your simulation and the real world, is it comparable?
Yeah. In this model, use river flow in from river from aquifer under the pit, and rainfall, average rainfall in this area, and fall out from a river, fall out and fall out from pumping well by dewatering, and evaporation by plant.
I see. All right. So you use the river model in this Mammoth Mine, yeah. So to simulate a similar type of flow.
Yes, I use a river across in each area. Yeah.
All right. So okay, thank you. Let's give a round of applause to Dr. Sarayoot for his presentation.
Okay, thank you.
Okay, thank you very much.
Everyone.
Yeah, thank you.